Video, I share my own understanding of thermodynamic explanations for spontaneity under standard conditions. These ideas appear in many parts of the textbook, meaning they combine aspects of enthalpy with entropy, particle level descriptions, a lot of different ideas. And when I say my understanding, I need to take a couple days. I need to think about it myself and consider how do I bring together the ideas. So I'm going to be discussing explanations for spontaneity. Spontaneous processes, be they a physical change, chemical change, they occur without needing to continue to add energy for them to take place. They just happen. Now, the explanations for those of things that just happen, uh, I don't think we can get more far reaching than that. Okay, it seems like as folks interested in natural processes that take place, being able to explain those, I don't know if there's a bigger question that we have that we're seeking to answer. The explanations might be thermodynamic or they might be involving kinetics. In this video here, I'm going to be sharing the explanations that are thermodynamic for cases that involve standard conditions. So with standard conditions, concentration of anything that we have would be 1 molar, gas is 1 atm. So as I'm thinking about when this will be useful or not, well, solids, if they have a phase change, going to be a liquid. Well, a phase change, as we know, does not include concentration in our description. So when I'm thinking standard conditions, things involving phase changes are certainly relevant. A chemical reaction, well, that does include concentration when we're trying to think whether that is spontaneous or not. So what we're going to be doing within here, we'll be thinking about examples where we could have phase changes or examples where we're doing apples to apples comparisons because all of the concentrations, all of the amounts are values of 1. That's what I'm thinking about for standard conditions. So how do I begin to explain that? Big picture starts with the Big Bang. My view is that all matter, energy, and space was initially in a very, very, very tiniest of tiny spaces. And ever since that initial point, everything is just moving out. Matter, energy, space itself, everything is moving out from that initial point. As time goes on, there's this spreading out, a dispersal of all of the matter and energy. That's going to be my storyline here. In this timeline, I would say that we're spectators. For the world around us, what's taking place is this dispersal. We're witnesses to this spreading out. Now, we can't take that whole timeline and run it in reverse. The universe is not going to turn around. Now, in this process, complexity can emerge. It can emerge naturally. I mean, if one looks around stars, planets, even the elements themselves are more complex than the starting material that they came from. We can cause this complexity to emerge. However, when we have this complexity emerge, these are false minima. They're occurring in the process of the overall dispersal, but they're not going to end up that way. They're not going to stay that way. They're not as dispersed as they will be when we reach the end of time here. I'd say we're all often most interested in the spontaneous emergence of complexity. We're more interested in the complexity of this flower here than we are when things are all spread out and nothing it seems to be happening anymore. So I would say as humans, as scientists, we're interested in the spontaneous emergence of complexity. So energy is going to be important. I'm thinking about both kinetic and potential energy. With kinetic energy, as a chemist, I'm thinking about how the particles of matter are in motion. And energy can be transferred between the particles with collisions. So if I grab this FET sim here, I'm going to add some particles to the container. So I'm initially going to add, let's say, 50 particles, and I'm going to put it at a very low temperature. Notice how small the speed is. I mean, we have it spreading out to fill the container, But if the temperature is a measure of the translational energy of these particles through space, put in the thermometer at a very small value. And we can see as they creep along. Now, not all the particles are moving at the same speed. I don't have a lot of energy available to be spread out, dispersed amongst all of these particles. It's being transferred in a collision, and there's not that much energy there. So let's rerun it right now. Let's rerun it. We'll again have 50 particles. We'll have it be at the maximum temperature. I again have a spreading out of the kinetic energy. Some are moving faster, some are moving slower. But as a collective, I definitely have greater kinetic energy, in this case with the higher temperature than with the low. Now, what happens if I combine the two? I have 50 that were at the high temperature, now 50 at the slower temperature, at the lower temperature. Notice I see a merging of the two. My thermometer is now reflecting a value somewhere in between. Due to the collisions right there, it's not like the fast particles always stayed fast and the slow particles always stayed slow. We saw a combining of the two. Even though every one of the interactions was non-directional, meaning it wasn't like they were always being transferred from the faster to the slower or from the slower to the faster. They could have had the collision change the kinetic energy in either manner. It still ended up giving me, though, an overall direction. Overall, the particles that were initially hot, that had the higher temperature, they end up as a collective slowing down, and the cold particles are speeding up. The energy is becoming dispersed. It's being spread out amongst all of the particles that I have. Now, are there times when these collisions could increase the kinetic energy of the higher temperature particle? Yeah, of course, that happens. But the spreading out, the fact that the hot particles don't just keep getting faster and faster and the slower ones keep getting slower and slower, it all comes down to the probability. The spreading out occurs because there are more options like that. So in this description that we have right here, Big Bang and the spreading out and the dispersal, we're just moving to the most probable state. Now, when I'm thinking about the potential energy, I know that when the potential energy decreases, the kinetic energy goes up, something we've seen with skate park. Now, it could even become a negative potential energy, but that's simply on what I'm defining as my reference potential energy value. Or the potential energy decreases when our electron moves back to the ground state and a photon is emitted. So I'm seeing a relationship between potential energy and kinetic energy. This move towards greater complexity of coming together, let's say, to form a bond, this would lower the potential energy, and this certainly occurs. But this is always accompanied by other aspects of the energy increasing. We can't conserve the energy and only have the potential energy decrease. If the potential energy is going down, we have to have the kinetic energy going up. That sim, I think, helps explain or illustrate that. So here's two oxygen atoms. We have a potential energy well. Will they stick together? There is a bouncing off because I can't just have the potential energy go down and have it stick together. Energy is being conserved here. So if my only description is involving potential energy, they're never going to stick together. So we might think, well, how might we have a bond formation actually take place? Consider this one. What if we had three particles involved? What if we had the two particles, like these two oxygen atoms, being attracted, coming towards each other, and then we had a third particle that could take away some of that kinetic energy? What if the collision was able to impart some kinetic energy onto this neighboring particle? This would be a way that I could conserve the energy, right? I could have the potential energy going down with the complexity being formed during the bond formation. And then I have the kinetic energy going up somewhere else within this. So this is what I'm thinking about, that when I have this lowering of the potential energy, let's not ignore that that's also leading to a spreading out or a dispersal of the kinetic energy, like with this neighboring particle. So a lot of times we'll see this word stability when we talk about chemistry. Well, what do we mean by its stability and where does that fit in? So I've got this view that as time goes on, we have the spreading out, a dispersal of the matter and the energy. There's examples where we would have a decrease in potential energy. Maybe that's bond formation, but the energy is still spreading out within this process. So, I mean, can particles move to a lower potential energy? Of course they can. The complexity that we observe is the particles having moved to a lower potential energy. When I say most of the elements are evidence of this, a sodium atom is more complex than the collection of protons and neutrons that led to it. Okay? Nucleosynthesis, the whole idea that we have the coming together to form more complex elements. Even the elements themselves are ones that have moved to a lower potential energy. But in a sense, consider how unusual this is. Let's say you're talking about two nitrogen atoms. These two particles stuck together compared to everywhere else they could possibly be in the whole universe. How rare is it to have those two actually stuck together at that moment in time? As time moves on, eventually they will no longer be together. It's just a false minima at the moment when they are stuck together. So in a sense, what's often being described as the most stable state, it's actually more improbable. It's so unusual to have those atoms bonded together compared to everywhere else they can be. Now, if you look up stability, uh, different definitions for it, this idea of when we think about things being stable, well, firmness in position somewhat applies to that. Continuance without change or permanence. Well, in my picture, nothing has permanence. Everything is spreading out over time. So I don't really think that this is really my worldview here. There's a chemistry specific one, resistance or degree of resistance to chemical change or disintegration. This, in a way, to me, is describing that lower potential energy. In some ways, I share with my students this view of stuck togetherness. When things are being described as stable, they are at a lower potential energy, they're more stuck together. But I'm wary of using the word stability because a lot of times students are going to equate stability with permanence. And in my storyline, that's not the direction the universe is headed. So we know that there's interactions between matter and energy. Matter, as far as how it can produce or use energy, well, we have endothermic and exothermic processes. Matter that is attracted and is coming together, that would be um, the that matter that is attracted and matter that is attracted and coming apart, that is going to be an endothermic process. We're moving to a higher potential energy, and you know the exothermic one. So we've got the idea that matter can be related to the energy that's involved. And we also have sort of the flip of that. How does energy now interact with matter? So let's think about this. This is going to be key for our understanding of spontaneity. So from everyday experience, I know that heat transfer goes from hot to cold. There's a direction to the heat transfer. Now, what is heat? I can think of heat at the particle level as disorderly motion, in contrast with work, which has a direction to it. So if I were to think about particles randomly moving and then interacting with other particles where we have a random motion, randomness interacting with randomness, that's my particle level description for what heat is. Work is something that has a direction. Imagine all of these particles moving left to right and striking the other ones. It can still impart kinetic energy, but that direction to it, that's my view of what work is describing. And both of these, Q and W, heat and work, are describing how I can change the energy. So what is matter going to do when it's heated? We have heat, interacting with matter, and we're asking, well, could it change the temperature? We have our description where the Q would be equal to the heat capacity of the matter and the change in temperature. So I'm thinking about this whole particle level description. I'm thinking about how temperature is referring to the translational motion as it moves in the X, Y, or Z direction. But there's other types of motion as well. The molecule can rotate, and that's going to depend on the shape of it. The rotations that are possible are different if I'm looking at a individual atom or if I'm looking at a molecule. We have our description here of what does it mean to have rotations for a linear molecule or a nonlinear one. Vibrations would be another way that energy can be used. So in my picture right here, I'm thinking about heat can interact with matter. A temperature change is describing a subset of this, the translational portion. But if the matter can do more things with the energy, it's going to have more terms contributing to its heat capacity. Energy, when it interacts with matter, is going to be distributed. It will be dispersed across the range of possible motions that that particle or molecule can have. And the heat capacity describes this. A larger heat capacity means that that matter can do more things, respond more to the energy. Now, where does this now fit with the idea of entropy? So Clausius, his description of entropy, he coins the phrase, change in entropy is equal to the heat that's transferred reversibly over the temperature. This equation describes that first idea that there is a directionality to heat flow. If we bring together two objects, a hot object and a cold object, we know what's going to happen. The hot one will cool down, the cold one will warm up. So if we were to transfer, for example, 400 joules of heat from one to the other, the entropy is going down from the hot object, it's going up in the one at the smaller temperature. If we do the math right here and combine it, we see that the total entropy is increasing as the hot object cools down and the cold one warms up. By describing this value right here, it's another way of saying that we have a direction to the heat flow. The same amount of heat leads to a larger entropy change when we have the temperature being lower. This is going to allow us to have an equation that turns out to be quite far-reaching concerning the heat flow. So this equation describes the observed direction of the heat flow. There's greater dispersal when the temperature is lower. The particles that we have that are initially there, the more limited their motion was initially, the smaller the temperature. For the same amount of heat that's added, the larger the change as far as how it can become dispersed, the larger the entropy change. This idea of designating it reversible, that's our way of having an approach for calculating this. When we do our calculations for this, we do ones where we're considering sort of this abstract ideal circumstance of always being at equilibrium and being able to look at it in terms of a reversible process. If heat is being added or removed, the entropy will always change. You can't add or remove heat without changing the entropy. You can use this equation and come up with derivations for other terms. It doesn't always have to be just in terms of the heat. You can use this and consider an ideal gas and come up with a derivation involving volume. How changes in volume would lead to a change in entropy, or in terms of pressure, or in terms of if you were to change the temperature, the corresponding heat capacity term. We have a case here where the entropy is defined as zero. Entropy of zero exists. It's when you have a perfect crystal with absolutely no particle motion at absolute zero. So we have an absolute entropy scale. We know what a zero value is. So all of these are important ideas as I'm thinking about entropy, and I'm going to be using it for spontaneity. So this idea of entropy values being absolute, they're absolute because we have a zero value that we can start from. For a given temperature, the molar entropy value describes how the matter has dispersed the energy in the form of particle motion. We said that energy is always spreading out. When energy interacts with a molecule, it's going to cause that molecule to move and use that energy in as many ways as it possibly can. The heat leads to a change in temperature, which is one type of motion, the translational motion. If there's other types of motion as well, then we have those accounted for within our heat capacity term. So I show here what happens if we are adding heat to different things, something with a small heat capacity like diamond. Diamond has a very small molar heat capacity. Many metals like lithium have a value very close to 3R because they all have the same types of motion. A larger heat capacity, something like O2, because more complex motion is available or possible for that. So if heat's added to each of these, I would see a larger change in temperature for the diamond because it has a smaller heat capacity. The motion isn't doing very much with the atoms within diamond. For the O2, for the atoms and molecules, there's a smaller temperature change because it is doing a lot more. It has a much larger heat capacity. It can do more than simply translate here. It can rotate in different ways. It has a lot more dynamics to its motion. The energy can be more spread out. When I'm thinking about O2, if I take it all the way on this absolute scale, from O2 solid as a perfect crystal at absolute zero, by the time I reach room temperature, I know that I've had not just the motion, I've had different phase changes as well. The energy is being involved in all of these parts. So when I'm looking at then standard molar entropy values at room temperature, all of these are a reflection of how much heat was added in order to take that substance from being a perfect crystal, 0 degrees Kelvin, all the way up to room temperature. What was the heat capacity along the way? Were there phase changes along the way? Recognizing that that heat can now be thought of as what does it mean in terms of its entropy? Notice how the heat capacity is showing up in both of these expressions here. It's involving one where we're interested in how much does the temperature change. It's the same heat capacity when we're interested in, well, what was the entropy change? If I look at O2, which is a larger value here, certainly than diamond, more heat was added to the O2 to bring it to this 25 degrees C from absolute zero than if I'm looking at something like water. It has a different amount of heat because it has a different heat capacity along the way. And its entropy then is larger. More heat has been dispersed in the O2 when it is at room temperature than certainly the diamond, for example. That's how we're understanding what absolute entropy values are. So this idea of then the dispersibility of energy, how it's getting spread out. So as time goes on, I'm thinking how energy is being spread out. It's becoming dispersed. It's doing more and more things when it interacts with matter. For some matter, the energy can't be spread out very much. It can't be spread out very much because the particle motion might be very limited in that matter. It can raise the temperature, but it's not going to be spread out and doing more and more different things. There's other examples, though, where the matter can disperse the energy much more. It has richer particle motion. Some matter disperses energy. In the way it moves, it uses this energy more than other matter. This is not only about the strength of the interactions or this resistance to chemical change or disintegration. The types of motion possible is also relevant. I have different types of rotations, for example, in H2 versus a helium atom. So it's not just how stuck together they are. Aspects of the shape are also important. Some matter, then, I would say has greater, to coin a phrase, dispersibility. And this is related in part to the factors that are affecting that heat capacity. How many different ways can it use the energy? How many different ways when the matter has energy provided to it, does that energy become dispersed? Now, I've been talking about specific aspects of matter. Specific matter, what does it mean to now consider both the system and the surroundings? So Big picture, a reaction or process that leads to this higher entropy means we have a greater dispersal then of the energy. We oftentimes, though, think about what does it mean in terms of a specific reaction or process, because that's what we can observe, that's what we can measure, that's where our thermometer might be. But in a way, that's a limited view of the process. As time goes on, that's spreading out in a dispersal, this is referring to the universe as a whole. When we're asking the question, well, tell me just about this small part of the system. Locally, how did the entropy change? That's really just us putting our own lens on a small subset of everything that is happening. I mean, we can choose what we're thinking about to be our system, but we're really witnesses to this overall process. So if we want to, though, think about that most local change in a particular system, how can we predict or understand what's going on? I think we can consider aspects of both the temperature and the concentration of the matter that's there. But since we're thinking about standard conditions, the concentration is not what we're thinking about. We're just thinking about how temperature then can affect this local entropy change. So, big picture, this timeline here, as it goes on, the entropy of the universe is going up. It includes both what we're calling the system and everything else, the surroundings. In a clever way, we can determine how the entropy changes in the surroundings by measuring the enthalpy change in the system. Because the entropy change for the surroundings, that's the heat that's involved and its temperature. To determine the heat that is involved, well, we can measure the enthalpy change for the reaction and use that now to get insights about the surroundings. So when we're looking at our Gibbs free energy expression here, that's what it's really just doing. It's still just describing is the overall entropy of the universe going up after we account for the things that are related to the system, the enthalpy and the entropy changes for the system. So as I think about this, let's say we have something take place in what we are defining as the system that's exothermic and it leads to greater entropy for the system. Well, this is always going to be spontaneous. This is the dispersal that we're talking about. We don't have to think about it any harder than that. This is describing something that as time goes on, it's always going to be spontaneous. Because this is the dispersal of matter and energy that we've been talking about. Now, this is not necessarily that common, however. Because it's something that's exothermic, it probably doesn't have a greater entropy. When I say these are opposites, when I'm thinking about an exothermic process, matter coming together to move to a lower potential energy, and in the process, increase the kinetic energy of the neighboring particles, I don't really have, I can't really square that readily. What does it mean to have the particles coming together in an exothermic way and yet somehow lead to greater entropy or dispersal right there? That usually doesn't happen. So I don't usually have things in this description. What if I'm interested in having heat flow take place in this local environment, in what I'm describing as a system? Well, we know how to have heat flow take place. That's easy. We know that the direction that heat flows, it goes from hot to cold. So if I want to think about this system right here and have heat involved, I can just pair it with the surroundings, the neighboring surroundings that are at a different temperature. If I want to have heat flow in or out, I just need to conceive what does it mean to have the surroundings be at a different temperature, because I know the direction of heat flow there. The overall entropy always increases when we think back to Clausius's description of our two objects in thermal contact. That's what's taking place if I want to have heat flow into or out of the system. It's all about the temperature of the two entities, the system I'm looking at and then the neighboring surroundings. Now, what if I want this heat flow and I want to think about this to make a reaction spontaneous? If I have a reaction that is going to be spontaneous because it is endothermic and the entropy of the system goes up, the temperature is going to be important. The temperature is going to be important because I need to consider the temperature that will allow heat to go into the system, and I have to think about how that temperature change affects the entropy of the surroundings. Same thing if it's exothermic. I know how I can have heat flow from the system into the surroundings. It's all about the temperature. But I have to consider how this will now be affecting the entropy of my system that's going down. I'm connecting this back to Clausius's way of thinking of how his description tells me the direction of heat flow. And I'm considering, if we think back, how the temperature was very important because that's affecting the magnitude of the entropy change. It leads me to say that for every process that is spontaneous due to heat flow, that it is going to have a temperature dependence. Every process that is spontaneous due to this heat flow has a temperature dependence because heat flow only occurs when I have this description here of differences in temperature. So if the process involves spontaneity due to heat flow, it's going to depend on the temperatures that I'm looking at. This right here is really my explanation for why any process is spontaneous or not under these standard conditions. It has entirely to do with the temperature, the corresponding then direction of the heat flow, and how that is now leading to an overall dispersal of energy for both the system and the surroundings in combination. When we're thinking about a chemical reaction, it's the same kind of phenomena here. As time goes on, there's a spreading out, a dispersal. But I'm thinking about it as matter interacting with other matter, reactants interacting with other reactants. But there's still an overall spreading out, a dispersal. We can't avoid that. And the surroundings are relevant as well. So if I'm thinking about calculating, let's say, the entropy portion for a reaction, and I'm just looking at the entropy change concerning the system, I can use these standard entropy values. If I look at these, I see that in this reaction right here, the water, that has the smallest entropy value. That, if we think back, takes the least amount of heat to bring that up to the 25 degrees C. The most heat was involved with the one with the largest entropy value. The energy is most dispersed within these per mole for the propane. And so we see that as this reaction takes place, there's actually a decrease in entropy because the energy was quite spread out with the propane, and it's less spread out here with the products. So this, in a way, seems like a contradiction. It seems like we're turning our timeline around, but we can't turn our timeline around. We have to look at the other feature on that, which was the enthalpy change. So if we look at our standard enthalpy of formation values, we can get an overall enthalpy change for this reaction, very exothermic. So if we think about what that then means to the surroundings, the entropy is going way up in terms of the surroundings. We see that there was a small entropy change for the system, but it's very exothermic, leads to a very large entropy change for the surrounding. So this universe entropy going up, that's what has to happen as we move along this timeline. At this particular temperature, the reaction's spontaneous because the energy that is produced as these products move to a lower potential energy, it leads to a large dispersal of energy in the surroundings. There would be a high enough temperature at which this is no longer spontaneous. Heat would no longer go into the surroundings. This is very spontaneous at 25 degrees C, but you can have a high enough temperature where within our timeline right here, it's no longer leading to a dispersal of energy because we no longer have heat flow go into this we no longer have heat flow going from the system to the surroundings because the surroundings would be at just too high of a temperature. and it no longer is net favorable in terms of the entropy. Now, these values right here are all delta values. Enthalpy, unlike entropy, is not an absolute scale. Now, this still works, right? We can still look at enthalpy changes. We can define our scale relative to the elements in their standard states. That's what our standard enthalpy of formation is. But in some ways, it's less easy to understand conceptually. Entropy is great because it's an absolute scale. We can still make enthalpy work, but we have this little difficulty, if you will, that we have to only look at the difference values. Now, when we're thinking about then the Gibbs free energy, the Gibbs free energy has the same conceptual information. It's just another way of saying as time goes on, we see a spreading out, a dispersal of the energy. Matter can interact with other matter, and we need to have that be taking place on this overall timeline, accounting for the surroundings as well. That description right there, thinking about the overall enthalpy and entropy change, that's what the Gibbs free energy is summarizing as well. The smaller, the more negative the delta G naught, the more favored it is. More favored meaning it's leading to a greater overall dispersal of the energy. Here's a description that shows the Gibbs free energy, the function of temperature, where it's looking at the phase change. This is from the Atkins textbook. It's showing the variation of the molar Gibbs free energy with temperature for 3 phases of a substance at a given pressure. The most stable phase is the one that has the lowest Gibbs free energy. And that as the temperature changes, that most stable phase changes. Let's say we're thinking about this transformation for H2O. We know that at a high enough temperature, we'll see a transformation from the solid to the liquid. When I'm thinking about the transformation from the solid to the liquid, this would be a dispersal of the energy for the system. It's becoming more spread out as I go from the solid to the liquid. But in order for this to occur, I need heat flow. To have this occur, I need heat flow from the surroundings into the system. In order for that heat flow to take place, I need the temperature large enough in the surroundings so that when I see this transfer, the entropy change in the universe is small enough so that overall net that still takes place. This will take place. Couple things that are interesting within this caption here. Stable is being described as the lowest Gibbs free energy. Stable is not being described as the lowest potential energy. Lowest potential energy in some ways would be only looking at the enthalpy term. Stability here, if we want to consider that as, well, what is the most likely? Notice how it is combining both the enthalpy and the entropy, and it's thinking not just about the system, but about the entire universe. You can reach a point, as you know, where you would have equilibrium. Is that the melting point? Is that the freezing point? You reach an equilibrium value where the change in the Gibbs free energy is 0. It's not spontaneous in either direction, or if you want to say it's equally spontaneous in both directions. When I look at some data here I show ones that are for aluminum and different compounds. A couple of thoughts within this one. Notice how it has data listed for molar heat capacity and the molar entropy. When I'm looking at these, there's a relationship between the two. It's what we've been thinking about. If something has a larger molar heat capacity, it leads to a larger molar entropy value. Going back to that, this is again this description. They have to go together because the molar heat capacity is related to that aspect of the particle motion, the variety of the way that the energy can be used by that particular molecule, that particular compound. And when something then has a larger molar heat capacity, the energy can be doing more things. It does more things. It's divided up across more aspects of particle motion, and that leads to a higher entropy value. Now, notice for both of these, the enthalpy and the Gibbs free energy, both of these are given delta values because we need, in both of these cases, we don't have an absolute scale for those. We don't have an absolute scale because we don't have an absolute scale for the enthalpy. So these are being given as values of formation. So it comes back to how we would write like a standard enthalpy of formation reaction, where we're looking at the elements in their standard state as the reactants, and we're making 1 mole of product. And notice how we're then defining those as having values of 0 for the elements then in their standard states. So I find within here, conceptually, like I said, the Gibbs free energy, it's describing this overall dispersal. But we have to do just a little bit more of thinking how the entropy is on an absolute scale. And when we're looking at ones involving the enthalpy or the Gibbs free energy, we're looking at differences. We can still put together the parts because we're still dealing with the state function. But conceptually, that's what's going on there. When I'm looking at Al2O3, I'm seeing something that has a very negative Gibbs free energy. It has a very negative Gibbs free energy because it is extremely exothermic in the process of making it. Making it, I mean, in comparison to the elements in their standard states. Al2O3 right here has a very negative Gibbs free energy. I would be describing it as very stable. But that stability there, we have to be careful with it. It is stable because it was so exothermic along the way that it has led to a dispersal of that energy into the surroundings. And I would also say, though, it's a false minima to say, okay, it's going to stay as Al2O3. It's not going to stay as Al2O3. As time goes on, the Al2O3 will itself become dispersed and be broken apart. So when I'm thinking about then the Gibbs free energy, this idea of reaching an equilibrium state is one that is maximizing the entropy of the universe. If I'm thinking about this reaching an equilibrium state, I could imagine, what does this mean at a particular temperature and I'm looking at H2O? What does it mean to reach equilibrium if I'm looking at, let's say, equilibrium between H2O solid and H2O liquid? Now, what Atkins is doing with this is he's describing the direction that it takes that spontaneously occur in order to reach equilibrium. And he's going on to say here that the Gibbs free energy gives us insight into how we reach this equilibrium. He's going on to say, provided the temperature and the pressure are constant. He's saying that because he's switching this discussion a little bit now. He's switching to non-standard conditions. He's thinking about what does it mean to account for the concentration of matter? What does it mean to reach equilibrium when we're looking at a constant pressure, at constant temperature, but we have different amounts there? That's what it means to consider non-standard conditions. Instead of looking at G naught, it's looking at the Gibbs free energy itself under non-standard conditions. But in order to make sense of that, I needed to first make sense of what does it mean under standard conditions. And my explanation for this under whether I'm under standard or non-standard is going to still be the same. It's both, in both cases, it's coming back to that timeline and saying what is unavoidable, what I can't reverse, is this overall dispersal of energy as time goes on. But that does not preclude complexity from taking place along the way. And in many ways, the complexity there, the false minima, that's what I'm interested in manipulating as a chemist.